Hello guys, welcome to our today's tutorial. Dr. Brennery, the universal data here. Alright, so remember we are still looking at benzene chemistry and the reactions. Now, we need to finish these reactions which fall under electrophilic aromatic substitution reaction. So today we are going to look at another part of benzene chemistry which is under the reaction, and this is what is known as Friedel-craft uh, alkylation. Friedel-craft alkylation. Okay, Friedel-craft alkylation reaction of benzene. So here reaction, I can just write like this, of benzene. Alright, so that's what we are going to look at today. Friedel-craft alkylation reaction of benzene. So this one is, let me just write a general reaction. A general reaction goes like this. This is when a benzene, so this is a benzene. When a benzene reacts with any alkyl halide, it can be methyl chloride, methyl bromine, ethyl chloride, ethyl bromide, or propyl, any, as long as it's alkyl halide. There's an alkyl group and also halide there. Then in the presence of a catalyst that is known as aluminium chloride, then we are going to have this, where this R, this is alkyl, is the one that is an electrophile there, then plus hydrogen halide. You get? So this is a general reaction of our Friedel-craft alkylation reaction of benzene. So when this benzene reacts with any alkyl halide in the presence of alkyl, or in the presence of aluminium chloride, which is the catalyst that speed up this reaction, then here, remember, it speed up the reaction without itself being changed. That is a catalyst. So we need to have the same aluminium chloride at the end of our reaction. Yes. So this is now the product, which is an alkyl or a benzene having attached with an alkyl group, which is an electrophile, plus hydrogen halide there. So let me just give you a quick, just a simple example that we can look at, and that one will help us to know the general mechanism, or that the mechanism of alkylation, which is FC alkylation reaction of benzene, or FC is just a Friedel-craft alkylation. All right, so okay, so this is now a question. This question you can find it in an exam, so pay attention. Okay, so I'm going to write like this. This is a benzene. Okay, this is a benzene. Then they say it reacts with so CH3, CH2, CH2, then chlorine like this. Then in the presence of aluminium chloride like this. So you say like that. Then here they say something like this, CH, then here CH3, then here CH3, so CH3 like that. Okay, so I need to write it well. So here it will be CH3 like that. Okay, CH3 like that. Okay, so this is now our product. Then they say write a mechanism. So let me just write the mechanism. So this is an exam question which we need to understand. That is a Friedel-craft calculation. This is propyl chloride. You see, it's an alkyl halide, because there's a propene, which is propyl group, and halogen, which is chloride, in the presence of our aluminium chloride, which is the catalyst. So now let's try to look at the mechanism. First of all, we know that we are looking at the electrophilic aromatic substitution reaction, which has 3 steps. The first one is generation of an electrophile. So now let's try to generate an electrophile. After generating an electrophile, we'll go to the next step. So an electrophile is this which has been added on the benzene there. So here it will come from this. So we're going to have this reagent, which is CH3, CH2, CH2 like this. Then here it will be chlorine. You get? So here it will be chlorine like that. Then I'm going to bring this, which is aluminium chloride, like this. So the way it is here, this one has got electrons. These electrons will come and attach itself where? On the, they will come and attach on the aluminium. Then it will give us this. So here I can write something like this, CH3, you get? CH2. Then here, C. If I want, I can write, okay, like this, just the same. CH2, then here CH2, then with chlorine, which has attached to aluminium, right, like this. So the charge on the aluminium here, it will be negative, then here it will be positive, like that. You get? So that's the product that we are going to have. After that, when you are having this one has a positive, it is attached to two bonds, which is from this carbon and this aluminium here. So when I reach at that point, I'm going to say this like this. So here there is chlorine with a positive here, then here there is aluminium like this with a negative. So what will happen is that this chlorine here, which has a charge, the bond will go. So I'm going to show that the bond has left. Okay, so here it will be like this. Okay, so this is an arrow. It will show like this. So here it will have a positive charge. Then plus here, which is chlorine, or I can just say aluminium with how many chlorine? 4. So here it will be negative like that. So that is the product that I have. So now this one, which is here, it is what is known as an electrophile. That is my electrophile there. But we need to understand that when we are dealing with alkylation, which is Friedel-craft alkylation, there will be a rearrangement in Friedel-craft alkylation of benzene. So why? Because here this is a formation of carbocation, which is, this is a carbocation. Then what we want is to have a stable carbocation. So you should know that here, this is the third degree, which is the tertiary carbocation, is more stable than the second degree, which is this is secondary carbocation. This one is more stable than primary carbocation. What do I mean by saying that? When you have a carbon that has a charge, which is a carbocation, is attached to 3 carbons, just know that it is tertiary, and that is the most stable carbocation. If it has that carbon which has a charge, which bears a charge, it is attached to 2 carbons, it is secondary carbocation, and it is more stable than primary carbocation. On the carbon bears a charge when it is attached to 1 carbon, that is a primary carbocation. So we concentrate on the one which is more stable. So here, when you are given such a question like this one is it is a propyl, but the charge is on the carbon and it is attached to only 1 carbon, that is the primary carbocation. Then, is there any modification we can do to make it more stable than the primary? Yes, it is. That is what is known as the hydride shift, hydrogen to shift. So here we are going to use hydride shift, but it's not always that you are going to be using hydride shift. Sometimes you can use methanide shift. Methanide shift is when a methyl group is shifting to make that carbocation to be very stable. But here, hydride shift is when now a hydrogen is shifting to make it more stable. So I'm going to just bring this CH. Okay, let me just use this like this. Okay. This is hydrogen, this is hydrogen, this is hydrogen, then here, this is hydrogen, this is hydrogen, then here, like this, like this. So here is positive like that, you get? So for me to make it more stable, at least the charge is supposed to be in between here so that it can be attached, the carbon that bears that charge can be attached to two carbons, and in that case we are going to say it is secondary than this one which is primary, which is unstable. So I'm going to get this carbon or this hydrogen, sorry. So the way I'm going to do now here is this N, you can get N of hydrogen on top of this one. So this one will come and attach here where there's a carbon there. Then what are you going to have? We are going to have this. Okay, you're going to have this. So here there will be a positive here. Then here there is a carbon. Then here like this. Have you seen? That is hydride shift, and it has become stable. It has become, yes, not more stable, but it has become stable than the one which we had, which is primary carbocation. But this one is now secondary carbocation. So this is the one that we are going to use as the electrophile. So there will be a rearrangement or the rearrangement of Friedel-craft alkylation of benzene. That's why we need to understand that. So now let me just go to the next. So I'm going to bring this. So step number two is 1 pi bond of benzene ring attaches the electrophile to produce non-aromatic carbocation. Non-aromatic carbocation, either they say carbocation or carbocation. So here I'm going to bring this CH3, then here CH, like here with a positive, then here CH3 like this. That's this. You've seen CH3 with the three hydrogen here, 1 hydrogen here, 3 hydrogen. These are the ones that have a 10. So 1 pi bond of so here is step 2, which is 1 pi bond of a benzene ring. You can see the benzene that we are using is this one exactly that I've written. That's the one that I'm going to use here. 1 pi bond of a benzene ring will attach here to the electrophile to produce non-aromatic carbocation, which is also known as uranium ion. So uranium ion, we need to form resonance, uranium resonance. So uranium ion is non-aromatic. So here we're going to say, okay, so it's a bit like this. So here when you are going to have this, which is CH, then here with C, then here CH3 like that. So here the positive will be here, you see, because the charge has the bond has gone, is the one that has attached itself to this. Then we're going to have the charge there. Then I'm going to say, okay, so this one is like this. Okay, so here we can form a uranium resonance by saying this bond can come here to stabilize this charge. So when it comes here, it will be like this. Then that one will be like this. The charge will be now here. So now we are going to say this one CH, then here the way it is CH3. Okay. Then here CH3 like this. But it will form 3 resonance form, which is the other one. It will be like this. So this can also come here, you get, to stabilize this charge. So here there will be a bond, here there will be a bond like this. The charge will be on top, and when the charge is next to the electrophile, then we are going to say we have 3 resonance form, which is those are uranium resonance. So we can put them in brackets to show that these are the same. So these are the uranium resonance, and the one which has more resonance form, it means it is more stable. That's what we learned. Don't forget about that. We said the transitional state is stabilized by resonance stabilization effect. If you remember what we discussed last time, this transitional state, it needs to be stable, stabilized, in order for the forward reaction to be favored. That's what we discussed, and this stabilization effect is called resonance stabilization effect. to make the transitional state be stable for the forward reaction to be stable. All right, so let's try to go to the last step. So the last step is we said, the last step is we need to restore the aromatic benzene. We need to restore the aromatic benzene. So here, this is not aromatic, it's non-aromatic carbocation. Let's try to restore benzene. So we said we're going to, let's try to look at the one that we've started with, is the same as this. Okay, good. So we're going to get N of this, but we are going to get the one which is on the first here, which is like this. So it will be like, okay, sorry. So it will be here, there will be a positive like this. Then here it will be like this, and CH. Then here, CH3, CH3. Okay. So we said for us to restore the aromatic benzene is to expose, the hydrogen that or that is on the carbon that bears an electrophile. That is an electrophile. Then let's try just to expose this hydrogen. When we expose it, then we're going to say, we're going to bring the base that we formed. Remember, the base that we formed is this one. Okay, don't forget, that is the base here. This is the base here, you get? Which is aluminium tetrachloride. So that's what we are going to use. So here is aluminium tetrachloride like this. So this is the one that is going to get this hydrogen, and this hydrogen, this bond will come and make a pi there. So it means that the electrophilic, the aromatic ring is restored. So here the product is going to be formed is like this, like this. So here it will be formed, this bond will be here, then here it will be like this, CH3, then here it will be CH3 like that. Then plus aluminium. So here we're going to say one chlorine here is the one that is going to react with hydrogen to form hydrogen chloride. So here it will be like this, plus what is this? Is aluminium chloride like this, because one chlorine has reacted with hydrogen. Then this is a catalyst, and we still have the same thing. We started with it and we are going to end with it. So that's how you go about Friedel-craft alkylation. Thank you so much, guys, for watching this video. Together we can. Dr. Brennery Wabonse, Dr. Brennery, the universal data. Thank you so much. Please subscribe and tell your friend also to do the same.